Hi, my name is Konstantin and I'm talking today about runtime monitoring of dynamic fairness properties. A good portion of the fairness research is interested in a static form of fairness, meaning how can I make sure that a classifier that has been trained on a fixed distribution is fair or not. By contrast, we are interested in dynamic fairness. That means the kind of systems that emerge once we've deployed such a classifier into an environment that has feedback loops. And how can we make sure that those systems remain fair and do not discriminate against certain subgroups? But why is this interesting? Well, it was shown that agents, which were proven to be fair in a static setting, could actually start hurting the groups they wanted to protect once deployed in a dynamic environment. To illustrate this, let me introduce you to a canonical example in the dynamic fairness literature, which is concerned with a lending problem. In this scenario, we have three components. First, we have a population. Each individual in this population is assigned a credit score ranging from 1 till 4. Moreover, each individual either belongs to group red or group blue. What you see in this box is the distribution of the respective credit scores for each group. Second, there is the bank. The bank takes an individual and decides whether it should grant or deny a loan. The third event is on the side of the customer, who either repays the loan or defaults. Those three components exist in a feedback loop. Let me make this more concrete by looking at a single iteration of this loop. In this particular instance, the member we've sampled from the population belongs to group blue and has credit score 2. Once sampled, the bank decides to grant the loan. Unfortunately, the customer fails to repay the loan and defaults. Thus, the credit score of the customer will be reduced by 1, resulting in a change in the average credit score of group blue by 0.1 from 2.8 to 2.7. Over time, this could result in a huge disparity between the average credit score of group red and the average credit score of group blue. In order to prevent this injustice, we are interested in estimating the current disparity between the average credit scores of the two groups. Because we are runtime monitoring, this estimation has to be made given a sequence of observations only. At each time step, our monitor will only observe the sample, the customer X, the decision of the bank, Y, and the outcome, whether the customer repays or defaults on the loan. To be a little bit more formal, the property we're interested in is the expected credit score of group red conditioned on every event that occurred into the past minus the expected credit score of group B conditioned on the past as well. Now, the goal of the monitor is to watch the system and compute a confidence interval capturing the changing true value of the property phi with desired probability. Let's move slightly away from this example and talk about the general class of systems that we are addressing. We again have our three observations, X, Y, and Z. We require that for each group G, the expected value of xt plus 1 conditioned on all the observations up until time t equals the expected value of xt conditioned on all the observations up until time t minus 1 plus some value, which is computed using a change function applied to the current observations at time t. Recall that in our lending example, this change function was plus or minus 1 divided by the number of people in the respective group. This brings us to the general monitoring problem. We are again interested in the disparity between the expected values of two groups. However, this time we are not interested in the expected value of xt, but in the expected value of some function gamma applied to xt, which, for technical reasons, we assume to be convex. So now, given this property, the task is to design a monitor M that, given the sequence observations OT, bounds the changing true value of the property phi with some desired probability. Let me briefly talk about the algorithm. First, we estimate the expected value of xt conditioned on everything that occurred up until time t, and we do this for each group. Then we compute the confidence intervals for those particular estimates. We push the confidence intervals through gamma And then we apply union bound and interval arithmetic to compute confidence intervals of this property. Let me quickly talk about how we achieve those confidence intervals. It turns out that estimating and computing the confidence intervals for the expected value of xt boils down to estimating and computing the confidence intervals for the expected value of x1. Therefore, the first step is to bound the distance between the expected value of x1 and our estimator. To accomplish this, we use dupe martingales, meaning we take the expected value of our estimator for the expected value of x1 and we slowly reveal more and more information, meaning we condition on more and more observations. Once we have accomplished this, we want to bound the difference between each entry in the martingale, meaning what is the distance between the martingale at time k plus 1 and the martingale at time k. Then, using this distance, we can apply a Zoomer's inequality to essentially bound the distance between the first entry in the martingale and the last entry in the martingale, which, coincidentally, is the same as bounding the distance between the expected value of x1 and our estimator. We constructed monitors for two canonical scenarios in the dynamic fairness literature, namely the lending and attention example taken from behaviour. In this particular instance, I will focus only on the lending one and I'll only show you one plot. What we observe here is the lending example where the average credit score of group red is significantly higher than the average credit score of group B, meaning at 3 points higher. Moreover, we can observe that our monitor, the shaded area, perfectly encloses the true value of the property phi. Also, we can observe that this is truly a dynamic setting because the average credit score or the value of the property changes over time. Lastly, I want to add that we ran this scenario with two different agents. The first one, indicated here in red, ensured that equal opportunity was satisfied, whereas the other one, here indicated in blue, maximized the reward for the bank. As it was already shown in behaviour, we can observe that the agent that maximizes the reward for the bank is actually the agent that decreases the bias in the credit score the fastest as compared to the equal opportunity classifier. This is partly due to the fact that the equal opportunity classifier overlends to people that have a high risk of defaulting on loans. Lastly, I want to add that we are not the first ones who had the idea of monitoring fairness. This was pioneered by Albergutti 2019. However, we partially extended their results to Markov chains in an upcoming paper. However, this paper is the first one of its kind that tries to tackle the problems found in dynamic fairness as described, for example, in behaviour. To conclude, I just want to add that our work is essentially trying to detect unfair behavior in deployed systems using simple, lightweight monitors. And the big question for the future is, how can we correct unfair behavior in time before huge disparities in, for example, credit score occur? Thank you for your attention.